In this lecture, we will be learning about soil and how to manage the soil in a sustainable manner. In this lecture, we will be reviewing how soils are made and some of the ways in which we abuse soil. Sustainable agricultural techniques generally enhance soil formation by encouraging natural processes. Improper or unwise strategies, however, can cause loss of soil and depletion of nutrients, requiring the use of fertilizers and other supplements to ensure soil fertility. The learning objectives for this portion of the lecture are to describe the 5 components of soil, and in particular, the component most critical to agricultural success, and to be able to describe the 2 leading causes of soil loss. It might just look like dirt to most of us, but healthy soil is a marvelous substance with astonishing complexity. Soil contains mineral grains weathered from rocks, partially decomposed organic molecules, and a host of living organisms. The complex community of bacteria and fungi are primarily responsible for providing nutrients that plants need to grow. Soil can be considered a living ecosystem by itself. Building a few millimeters of soil can take anywhere from a few years to a few thousand years. Terracing, as in these Balinese rice paddies, can control erosion and make steep hillsides productive. These terraced rice paddies have produced 2 or 3 crops a year for centuries because the soils are carefully managed and organic nutrients are maintained. With careful husbandry that prevents erosion and adds organic material, soil can be replenished and renewed indefinitely. So what is soil? Soil is a complex mix of 6 components. 1. Sand and gravel, mineral particles from bedrock either in place or moved from elsewhere as it's wind-blown sand. 2. Silts and clays, extremely small mineral particles. Many clays are sticky and hold water because of their flat surfaces and ionic charges. Others give red color to soil. Dead organic material. Decaying plant matter stores nutrients and gives soils a black or brown color. Soil fauna and flora. Living organisms, including soil bacteria, worms, fungi, roots of plants, and insects, recycle organic compounds and nutrients. Water. Moisture from rainfall or groundwater, essential for soil fauna and plants. And 6. Air. Tiny pockets of air help soil bacteria and other organisms survive. Soil ecosystems include countless organisms that consume and decompose organic material, aerate soil, and distributes nutrients through the soil. This is a sample soil profile showing common horizons. Soils vary greatly in composition and thickness of layers. Below the B horizon, there is generally a C horizon of weathered rock, sand, or other parent material. Depth is marked in 10 centimeter increments. Soils are largely differentiated according to the thickness and composition of their upper layers. The U.S. Department of Agriculture classifies the thousands of different soil types into 11 soil orders. 3 important soil types are 1. Mollisols, for example, have a thick, organic, rich A horizon that develops from the deep, dense roots of prairie grasses. Alpha soils have a slightly thinner A horizon with slightly less organic matter. Alpha soils develop in deciduous forests where leaf litter is abundant. Iridosols of the desert southwest have little organic matter, and they often have accumulations of mineral salts. Organic rich mollisols and alpha soils dominate most of the farming regions of the United States. However, at least half of the original depth has been lost to careless farming techniques. Temperate grassland soils tend to have a thick, soft, organic rich A horizon. Arid land soils may have little or no workable A horizon, as in this Libyan valley. This figure shows the distribution of cropland in the United States by county. Dark blue areas especially highlight the fertile farm belt of the Midwest and Great Plains, as well as Mississippi River bottom. Agriculture both causes and suffers from environmental degradation. The International Soil Reference and Information Center in the Netherlands estimates that every year 3 million hectares of cropland are made useless by erosion, 4 million hectares are turned into deserts, and 8 million hectares are converted into non-agricultural uses, such as homes, highways, shopping centers, factories, and reservoirs. Over the past 50 years, some 1,900 million hectares of agricultural land, an area greater than that now in production, have been degraded to some extent. About 300 million hectares of this land are strongly degraded, with deep gullies, severe nutrient depletion, or poor crop growth, making restoration difficult and expensive. Water and wind erosion cause a vast majority of global soil degradation. Chemical degradation, a secondary cause of soil degradation, includes nutrient depletion, salt accumulation, acidification, and pollution. Most erosion is more subtle. Sheet erosion removes the thin layer of soil as a sheet of water flows across a nearly level or gently sloping field. When small rivulets of running water form and cut small channels in the soil, the process is called rill erosion. Where rills expand to form bigger channels or ravines, too large to be removed by cultivation, we call the process gully erosion. Stream bank erosion also is a problem in farmland streams, where soil washes away from stream banks. Cattle and other livestock often accelerate stream bank erosion as they trample and graze down the vegetation that holds a bank in place. Sheet and rill erosion cause most soil loss on farmland, even though this process is often too gradual to notice. Studies in Iowa farm fields have found areas with as much as 50 metric tons lost per hectare during winter and spring runoff, more than 12 times the rate considered tolerable or officially acknowledged by state soil scientists. That loss represents just a few millimeters of soil over the whole surface of the field, but repeated years of storms and spring runoff are gradually sending Iowa's productive capacity downstream to the Gulf of Mexico. Land degradation affects more than 1 billion hectares yearly, or about two-thirds of all global cropland. Globally, erosion by water accounts for about 56% of soil loss from fields. Wind can equal or exceed water in erosive force, especially in dry regions and where vegetation is sparse. When plant cover and surface litter are removed from the land by agriculture or grazing, wind lifts loose soil particles and sweeps them away. Intensive farming practices are largely responsible for this situation. Row crops such as corn and soybeans leave soil exposed for much of the growing season. Deep plowing and heavy herbicide applications create weed-free fields that look tidy but are subject to erosion. Farmers, under pressure to maximize yields and meet loan obligations, often plow through grass-lined watercourses, low areas where water runs off after a rain, and pull out windbreaks and fence rows to accommodate the large machines and to get every last square meter into production. In extreme conditions, wind-blown dunes encroach on useful land and cover roads and buildings. Over the past 30 years, China has lost 93,000 square kilometers, about the size of Indiana, to desertification or conversion of productive land to desert. Advancing dunes from the Gobi Desert are now only 160 kilometers, 100 miles from Beijing. Every year, more than 1 million tons of sand and dust blow from Chinese drylands, often traveling across the Pacific Ocean to the west coast of North America. Since 1985, China has planted more than 40 billion trees to try to stabilize the soil and hold back deserts. Globally, erosion by wind accounts for another 28% of global cropland. In summary, soil is a complex, living, biological ecosystem. With careful husbandry, that prevents erosion and adds organic material so soil can be replenished and renewed indefinitely. Soils are lost annually to erosion, desertification, and conversion to non-agricultural uses. Water and wind erosion cause a vast majority of global soil degradation. Chemical degradation, a secondary cause of soil degradation, includes nutrient depletion, salt accumulation, acidification, and pollution.